Space and time complexity are extremely important ideas in algorithms and data structures, and in general in computer science. These are extremely interesting and important ideas that we will keep visiting when we learn machine learning. But this idea is not in machine learning or data science. These are ideas in algorithms and data structures. Here, DS doesn't mean data science; it means data structures here. Now, in a nutshell, there is a lot of theory here. I cannot cover all the concepts in space and time complexity in a 20 or 30-minute video. So this area itself is like a whole chapter in most books, in most algorithms books, right? So I will try to give you an introduction here. In this section, I'll try to give you an introduction to this to the ideas of space and time complexity. This is by no means an exhaustive. This is not an exhaustive or a full explanation of these ideas. Okay, this is not exhaustive. I just wanted to make this clear. This is just an introduction. Now, what space and time complexity mean is very important. This is one way, this is one mathematical way for us to measure. This is important, to measure or quantify, how much time does a program, to measure how much time a program or an algorithm, right, or a solution that you have written takes. So it measures how much time and space a program or an algorithm or a solution takes. So I think it's better to understand this concept with an example instead of just talking about it in theory. So let me pick up an example here. Imagine if I have a list. Okay, this is how we'll introduce the concept. Imagine if I have a list. This is index 0, index 1, so on and so forth, index 2, index n minus 2, and n minus 1. So this is a list of size n. This is a list of size n. This is important. It's a list of size n. So we are using general numbers. Of course, n could be 100, n could be 100, or it could be 1000, or it could be 10,000, any number. But we are just using a generic number n. So this is a list of size n. Now imagine there is a problem. Okay, the problem here is given a number q, here q stands for query. Given a query number q, you want to find, so the problem is find if q exists in my list L. Okay, let's assume this list is L. So amongst all these numbers, amongst these n numbers, does q exist or not? Right? That's the problem we want to solve. What is one of the simplest solutions for this problem? One of the simplest solutions. What can I do here? Let's understand. I will basically check the first number here and say, oh, suppose, let's take examples here. That will make life simple. Let's assume this is 3, 2, 6, 5, 4, 3. Let's say some of these numbers could repeat, of course. 1, 32, right? So on and so forth, 56 and 31, right? So those are the numbers. Now let's assume my q here is equal to 32. Okay, now I want to understand whether 32 exists in this list or not. How do I do that? It's fairly simple. First I go to the 0th index. Here, and I compare 3 with 32. 3 is not equal to 32. So now I go to index 1. 2 is not equal to 32, right? I keep doing this, and at some point I'll come here. This is my index 3, 4, 5, 6, 7. At index 7, right? At index 7, I see 32. Now this 32 and this 32 match. So I will say that, yes, 32 exists. 32 exists in my list L at, I can say, index 7. Right? So very simple. Now imagine. So this is the first case. This is case 1. Now let's take case 2. What is case 2? If q is not present in the list, let's assume q equals to 325, and let's assume 325 is not there in the list. Then what happens? You will keep checking. You'll keep checking through all the elements in the list, and you'll finally say that 325 does not exist. 325 does not exist in list L. Right? Now, similarly, let's take the third case. Let's take the third case. Let's assume, so this is case 1, this is case 2. Let's assume the third case is q equals to 31. In that case, you'll go through each of these elements, and at the last element, you'll say, yes, 31 is present. 31 exists in L at index n minus 1, right? There are 3 cases here, right? I've just taken 3 cases. One case where the query point that you wanted exists somewhere in the list. The second case where the query point does not exist in the list itself. The third case where the query point is the last number. Now let's take case 1. Okay. For case 1, how many comparisons did we do? We have total of n numbers, right? Let's not forget that. What is the most basic operation here? Comparison. How many comparisons did we do in case 1? We did 0, 1, 2, 3. We did 8 comparisons, right? In case 2, how many comparisons did we do? We did n comparisons. In case 3, also we did n comparisons, right? So in the worst case, what is happening in the worst case? In the worst case, you end up doing about n comparisons to say whether an element exists or not, right? So now I can say if a list has n elements, right? The solution that I just designed here, what was my solution? My solution was check each element in list L, right? One after the other, sequentially, right? Sequentially. This is my solution. Now this solution, if I have n elements, how many, now the question here is this, how many comparisons are needed? Now, each comparison takes some time. See, look at it. Each comparison takes some time. Now, if you have n elements, the question here is, how many comparisons are needed? You need roughly n comparisons in the worst case. So you need n comparisons in the worst case. Of course, best case, you could get extremely lucky and your number could be here. Then you just needed 1 comparison, right? But in the worst case, you needed n comparisons, right? What about the average case? Okay, let's write about the best case. If you're really, really lucky, you can just get away with 1 comparison. But of course, this happens very seldom, right? On an average, so now I can compare that. On an average, if you give me any number, some numbers will be present, some numbers will be absent. I would require roughly about n comparisons, approximately n comparisons. Of course, this proof, I'm not doing it rigorously, I'm just stating it here, right? Now look at it. As n increases, right, my number of comparisons, I write number as a hash, right? My number of comparisons also increase proportional to n, right? Imagine if n was 10, my number of comparisons is 10. If n is 100, my worst case number of comparisons are 100. If n equals to 1000, this will become 1000. Similarly, if n equals to 10 million, this will also become 10 million, right? Which means as n increases, my number of comparisons are also increasing proportional to n. So can I say that my number of comparisons are proportional to n? This symbol in mathematics means proportional. This symbol basically means proportional. Those of you who studied physics in your 11th grade or something like that, you'll understand that force is proportional to mass and force is proportional to acceleration. You must have learned this in Newtonian physics, right? Same terminology. Your number of computations is proportional to n. And each comparison takes some time. Of course, there is some other time here. Like for example, when I write code, there will be some time that it will consume. But in general, I can say my number of computations is proportional to n. So let's look at some code here so that we get an understanding. Okay, so let's look at some code here. Sorry. Okay, here is the code. Okay, I'm creating a NumPy list. I have a list of 100 numbers here. Okay, and I'm randomly shuffling them, because when I create a list, what do I get? I get numbers which are sorted, right? I get sorted numbers like this, but I want to shuffle them. I want to jumble all of these numbers in random order. Okay, now I get this list. Now my list L is like this. It's not at all sorted. Remember, my list L is not sorted, right? It's a randomly shuffled list. Now in this list, I want to find whether a query number exists or not. Now here is the simple code for this. Okay, so let's see how we do it. Okay, so I say q equals to 31. Okay, this is my query point. Let's assume this takes 1 unit of computation, 1 unit of time, some small amount of time, of course. Now I'm declaring a variable called is found. This also takes 1 unit of time or computation. So the more computation means more time, right? So let's assume all of this takes 1 unit of time. This unit could be a microsecond or a nanosecond, whatever it is. Now I'm starting a for loop, right? This for loop, in this for loop, what am I doing here? I'm checking if this for loop goes for each element in L, right? This for loop says each element in L, if element equals to 31, print and break the loop, get out of the loop. And you're saying you're changing the is found variable to true. At the end of it, if this doesn't break at all, if is found continues to be false, you'll say the element is not found. Now let's look at the fun part here. The fun part in this is this. Okay, let me change the color here so that, okay, this takes 1 unit of time, this takes 1 unit of time. Each of these also takes 1 unit of time. Let's assume, because this is simple one line statements, right? So let's assume all of them takes 1 line of time, right? Or 1 unit of time. The catch here is this section of code, this for loop can run n times. If I have n elements in a list, let's assume the length of my list, let's assume my L is of length n. Then even though each of these lines takes only 1 unit of time, okay, my 1 unit of time could be roughly about 1 nanosecond or 1 microsecond, depends on your processor, but roughly 1 unit of time. But the important part is all these lines, because look at it this way here, right? This is a for loop, which means first it will check with the first element, right? Run through all these steps, and then it will again go up, change it to the next element, again run through all the steps, and repeat this n times, right? So this line, since it's repeated n times, this is run, and this consumes totally n units of time. This also consumes n units of time. This also consumes n units of time. This also consumes n units of time. At the end of the program, what is the total time? If I want to write the total time, okay, it is this 1 plus 1. Okay, it is 1 plus 1, 2 plus n plus n plus n plus n. 4 into n, 4 n's here, right? Plus 2. Right? So what is the total time here? 4n plus 4 units of time. Units of time. Right? This is my total time. Let's remember this number because this is very useful now. Okay. So the total time I have, the total time is 4n plus 4, where n is the number of elements in your list L, because this loop runs for every element once, right? And hence n times. Now, if I want to say, so it's 4n plus 4, right? Actually, I don't care about these constants. Okay, if I want to write this as proportionality, can I say that my total time is proportional to n? From this formula, can I say, I'm just looking at proportionality. What does proportionality mean? As total time increases, or as n increases, the way to look at it is, as n increases, my total time also increases proportionally, right? So that's an important idea. So instead of saying my total time is 4n plus 4 units of time, I could just say, in computational complexity, we simply end up saying that my total time complexity, I end up saying that my time complexity, or the time it typically takes to run this type of algorithm or solution, is order of n. This n comes from this proportionality. Okay, so let's go back and understand one more idea. Suppose if my code takes order, so okay, let me change the color here. So imagine if my code takes 4n plus 4 steps, 4 time units. Okay, this is the number of time units it takes for a code. Okay, let me explain you some simple ideas here. And this is what you write as time complexity. Okay, when you have something like this, right, for a list of, let's say, for an input of size n, if it takes 4n plus 4, then I say that my time complexity is order of n. Now let's say if I have something like this, if I have 3n square plus 2n plus 4, let's assume if I have something of input size n, this is some other code, not this code, right? Not your finding the largest element, some other program has, when you compute the time units, the way we did here, we compute the number of time units here, right? If you exactly do that, let's assume we are getting 3n square plus 2n plus 4. Let's just assume. Now what do we do when we compute time complexity is as follows. We take the largest, say, so this you can think of it as 4 into 1, right? This you can think of it as 4 into 1. This you can think of it as 2 into n. This is 3 into n square. Now n square, because n is a number, right? N square is greater than n. I'm just discarding all the constants here. They're not very important. Which is greater than 1, greater than equal to 1. Now pick the one that is largest here. N square is greater than equal to n, because n is an integer, right? Take n equals to 1. Then what is your n square? Your n square is 1, which is equal to 1, which is equal to 1. If your n is 2, what happens? Your n square is 4, which is greater than 2, which is greater than 1, right? So n square is always similarly, take an example, right? Here, take n equals to 3. This is 9 greater than 3 greater than 1. So just ignore the constants which are there here. Your n square is greater than n, which is greater than equal to 1. So now what I say is, if a program or an algorithm or a solution takes 3n square plus 2n plus 1, I write its computational complexity as order of n square. Because I take the largest term here. I ignore the rest of them. I take the largest term here and put the largest term here, right? Similarly, let's take another example, okay? Imagine if I have my time units here and my time complexity. Okay, so imagine if I have an input of size n, and if it's taking me, let's say, 4 times log of n plus 3. Okay, there will be cases where we will get log of n. We'll see that in a while in this section. Okay, so let's assume I have this. Then what happens? Then there is a fun thing. As we said, neglect the constants. So I have log n. Obviously, log n is greater than equal to 1. Right? So we say the complexity is order of log n. So you will mostly find order of n square, order of n cube, order of n, order of log n. So what happens if your input is of size n, but it only takes you, let's say, five operations to do it? Then 5 can be written as 5 into 1. You neglect this and you write it as order of 1. Okay, for this you write it as order of 1. So these are the typical types of complexities that you will find. Typical, not necessarily only these. You'll find things like order of n log n. You'll find all these types of complexities typically written. Okay, so people either write log or lg. It depends on the short form they want. Okay, by the way, this video is just a very little introduction to computational complexity. This is not the full story. So this is only an introduction so that we understand, when we learn machine learning algorithms, some basics of time complexity and space complexity.